Welcome, ladies and gentlemen, to our online lecture looking at identifying mixtures, separating mixtures, and then classifying forms of matter. So this will be kind of a two-part lecture. The first part will work with some examples related to physical properties and changes, and then we're going to start digging into specific types of matter. So our next upcoming lab that we've started talking about, or we'll be talking about soon, is looking at how to separate the parts of a mixture. Therefore, we need to know what a mixture is. So when you look at the images below, you'll see several different real-life examples of mixture. So it's anything that's blended physically of two or more components. So we see the salad on the left, the chicken soup in the middle, and atmospheric air on the right. So the model there shows there's water vapor, there's nitrogen, there's oxygen. The CH4 is methane coming from the animal that you see over there. And there's a little bit of carbon dioxide as well. So what does it mean if something is blended physically? So blended physically means that when those substances are combined, they remain what they are in the mixture. So they're more or less occupying the same space, and it may look all evenly distributed, but the individual substances that were put together are still there in the same chemical makeup that they were to begin. Now we can classify mixtures based on the distribution of their components. That means we can look at how they are arranged within their space. So we look at two different terms to describe this. We have heterogeneous mixtures, and the prefix hetero should make you think different. Homogeneous mixtures are where they have the same distribution. So what is the same is how the particles and the materials are dispersed. So if we have something like chicken noodle soup, imagine that you take a spoonful out of the soup. Imagine that you have a piece of chicken, a carrot, and a noodle, and you have some broth in there with it. And maybe the next spoonful, you get all chicken in with the broth. That's kind of showing us that the composition is not uniform. Every time you take a sample out, you're not getting the same distribution of particles. Now, a homogeneous mixture, think of something like an olive oil, where there are different types of compounds in it. A vinegar is often a solution with water and acetic acid. If you have something like Kool-Aid, that's one of my favorite examples. When you have your Kool-Aid, you've got your sugar, you've got your flavor, you've got your dyes that give it those fantastic colors. All of that looks the same. When you pour a well-made cup of Kool-Aid, every single cup you pour is going to taste the same because all of the material within it is evenly distributed. So the Kool-Aid is a great example of a homogeneous mixture, and the chicken noodle soup is a good example of heterogeneous. It's the distribution that is different. Solution is a synonym for homogeneous. So please write that down. That is your spoken but not written word of the day. So solution is the synonym for homogeneous mixture. An interesting piece of that, a solution doesn't have to be liquids. You can classify something like an alloy as a solution when you have one type of metal mixed with the other. Remember when we watched Hunting the Elements on that day I was gone? I know it was a little bit hectic, but the alloy in the examples of making the bells, when you have the mixtures of the metals, when it's evenly distributed like that, it would classify as homogeneous. So one of the things we can do with a mixture, because it's physically combined, is we can separate out those things back into their individual components. It's the physical properties of the substances that we base our separation techniques upon. So filtration would separate a solid from a liquid. Think of coffee. When you're making your coffee, the water will go through the coffee filter, but the solid coffee bean granules do not. Distillation is a way to take advantage of different components and boiling and melting points. So when you distill water, there are many substances dissolved in water that can't transition to a gas when the water does. And so the water gets separated and turns to steam, whereas the solid particles get left behind. You might notice this too if you have a cup of water that evaporates and you see that white film left behind. Those are all the dissolved particles within the tap water. So this is the point where we're going to shift ideas a little bit. So prior to this, we were talking about separating mixtures and what they are. Now we're going to start identifying those components or substances that may be present within a mixture. So of the forms of matter we've talked about so far, we've hinted at this idea of pure substances and mixtures. Those are two major categories. When we're looking at pure substances, we are looking at elements and compounds. So element is our simplest form of matter, and all of the atoms are of the same kind. When I have a compound, it's going to contain two or more elements chemically combined, not physically, chemically, in a fixed proportion. Think about a molecule of water. For every one oxygen, there is always two hydrogen. That is a fixed proportion. If I would have H2O2, that is a completely different type of substance. If you're into funny jokes like I am that are related to science, there might be a joke in your future that you might recognize related to H2O2. Now, when we look at the types of properties that are in compounds compared to their elements, they're often very different. Think for a moment of table salt, sodium chloride. Sodium as a metal is extremely reactive. We actually have to store it in oil to prevent it from reacting with oxygen or water vapor in the air. Chlorine as a gas is very harmful and actually used as a disinfectant because it's so good at killing things. But when the two react together and become a compound, sodium chloride is really safe, so much so that we eat it and it's used to preserve our food. Very different set of properties when they're in the compound form. So let's say we wanted to break apart a compound. It can be done, but the chemical structure is changed when that occurs. That means in order to break it down, I have to put it through some kind of chemical change. An element cannot be broken down. It is the simplest form of matter I can have. I can't break apart the atoms and still have those basic forms of matter. Now, unlike a mixture, which can be physically separated based on things like boiling point or that sort of thing, a chemical compound has to be broken apart chemically. So what I get at the end is a different chemical makeup when I'm done. So the next example is really going to look at that in the form of water. When I compare the physical change of water to its chemical change, we can see that something distinctly different is happening. If I have water that's being heated to the point where it turns into water vapor, that's simply going from a liquid to a gas. It's still H2O molecules. If I go through a chemical change, for example, if I use electricity as my form of energy, it can disrupt the bonds holding the hydrogen atoms to the oxygen atom, and in that case, I'm going to get out hydrogen gas and oxygen gas. H2 and O2 as separate molecules are not the same chemically as the water was to begin with. This is a different kind of change. So as we consider the different types of compounds we work with, there is a distinct difference between state changes, which are physical, and chemical changes, which involve changing the chemical makeup of the matter.